Qwest Technical Reference 778 outlines specific grounding requirements for their systems. The grounding electrode conductor, or GEC, must be connected to the main bonding jumper located within the electrical panel. The grounding electrode conductor material needs to be either bare or insulated copper wire, or solid aluminum wire. The size of the grounding electrode conductor needs to be determined according to the table outlined in section 250.66 of the National Electrical Code, or NEC. Finally, the grounding electrode conductor must be routed directly to the grounding electrode, ensuring there are no splices or breaks along its path. Regarding the use of solid versus stranded wire for grounding, the National Electrical Code does not explicitly state a preference for either type. However, stranded wire is frequently chosen for grounding applications due to its greater flexibility and ease of handling compared to solid wire. The term Uffer is informal terminology referring to a grounding rod driven into the earth. It is thought to have originated in the early days of electrical systems when driving a metal rod into the ground was the primary method for establishing a ground connection. The name may have been derived from the sound produced by a hammer striking the rod as it was being driven into the earth. Now let's delve further into the details of grounding systems and the relevant code requirements. Grounding is a critical aspect of electrical safety, designed to provide a low impedance path for fault currents, thereby minimizing the risk of electric shock and equipment damage. The National Electrical Code, specifically Article 250, provides comprehensive guidelines for grounding and bonding electrical systems. The grounding electrode system serves as the foundation for effective grounding. It typically comprises one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode conductor connects the grounding electrode to the electrical system's grounded conductor, typically at the service equipment. As previously mentioned, section 250.66 of the NEC dictates the required size of the grounding electrode conductor based on the size of the service entrance conductors. Proper sizing is essential to ensure that the grounding electrode conductor can safely carry fault currents back to the source. The main bonding jumper is a crucial link that connects the equipment grounding conductors to the grounded conductor at the service equipment. This connection ensures that all metallic parts of the electrical system are at the same potential, minimizing the risk of voltage differences that could create shock hazards. Equipment grounding conductors provide a path for fault currents to return to the source from non-current carrying metallic parts of electrical equipment. These conductors can be wires, conduits, or other approved metallic pathways. Effective equipment grounding is vital for clearing ground faults and preventing electrical shock. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electrical shock by detecting ground faults and quickly interrupting the circuit. GFCI protection is required in various locations, such as bathrooms, kitchens, and outdoor areas, where the risk of electric shock is higher. Bonding refers to the practice of connecting metallic parts of an electrical system together to create a low impedance path for fault current. Bonding helps to minimize voltage differences and reduce the risk of electrical shock. Common bonding methods include using bonding jumpers and bonding locks. The grounded conductor, often referred to as the neutral conductor, is intentionally grounded to provide a reference point for the electrical system. The grounded conductor carries current under normal operating conditions and also provides a path for fault currents to return to the source. The ungrounded conductors, often referred to as hot conductors or phase conductors, carry the electrical current from the source to the load. These conductors are typically insulated and should never be connected to ground. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes, power outages, or other disturbances. SPD divert surge currents to ground, preventing them from damaging sensitive electronic components. Proper grounding is essential for the effective operation of surge protection devices. In addition to the general grounding requirements outlined in the NEC, there may be specific grounding requirements for certain types of equipment or systems. For example, data processing equipment, sensitive electronic devices, and emergency systems may require special grounding considerations to ensure reliable operation and minimize the risk of damage. Ground testing is a method used to verify the effectiveness of a grounding system. Ground testing involves measuring the resistance between the grounding electrode and the earth. A low resistance value indicates a good ground connection, while a high resistance value may indicate a problem with the grounding system. Regular ground testing is recommended to ensure that the grounding system remains effective over time. Grounding inspections are conducted to ensure that an electrical system is properly grounded and meets the requirements of the NEC. Grounding inspections are typically performed by qualified electrical inspectors. Deficiencies identified during a grounding inspection should be corrected promptly to maintain the safety and reliability of the electrical system. There are several common grounding mistakes that should be avoided. These include using undersized grounding conductors, failing to properly bond metallic parts, neglecting to provide GFCI protection in required locations, and improperly installing surge protection devices. Avoiding these mistakes is essential for ensuring the safety and effectiveness of an electrical system. When working with electrical systems, it is essential to follow safe work practices to minimize the risk of electrical shock or injury. These practices include energizing circuits before working on them, using appropriate personal protective equipment, and following lockout/tagout procedures. Safe work practices are vital for protecting workers from electrical hazards. The National Electrical Code is regularly updated to reflect changes in technology and best practices. Staying up to date on the latest NEC requirements is essential for electrical professionals. Continuing education courses, industry publications, and online resources can help electrical professionals stay informed about the latest code changes. Grounding is not only a matter of code compliance but also a matter of safety. A properly grounded electrical system protects people from electrical shock, reduces the risk of equipment damage, and improves the overall reliability of the electrical system. Therefore, it is essential to prioritize grounding in all electrical installations. The use of proper grounding techniques can also prevent electromagnetic interference or EMI, which can disrupt the operation of sensitive electronic equipment. Effective grounding provides a low impedance path for EMI currents, minimizing their impact on equipment performance. Proper grounding is also essential for lightning protection systems. Lightning protection systems are designed to protect buildings and structures from lightning strikes. Grounding is a critical component of a lightning protection system, providing a path for lightning currents to safely dissipate into the earth. In some cases, specific grounding requirements may be mandated by local codes or regulations. It is essential to be aware of and comply with all applicable local requirements. Local electrical inspectors can provide guidance on specific grounding requirements in a particular area. Utility companies also have specific grounding requirements for connecting to their grid. These requirements may vary depending on the utility company and the type of service. It is important to consult with the utility company to ensure that grounding practices comply with their requirements. The design of a grounding system should consider the specific characteristics of the site, including soil conditions, the presence of underground utilities, and the proximity to other structures. A qualified electrical engineer can assist in designing a grounding system that is appropriate for a particular site. The maintenance of a grounding system is essential for ensuring its continued effectiveness. Regular inspections and testing should be performed to identify and correct any problems with the grounding system. Maintenance activities may include tightening connections, replacing corroded components, and verifying ground resistance. The cost of grounding should be considered as part of the overall project budget. While grounding may represent a relatively small portion of the total project cost, it is a critical investment in safety and reliability. Cutting corners on grounding can have serious consequences. Proper documentation of the grounding system is essential for future reference. Documentation should include drawings, specifications, test results, and maintenance records. This information can be valuable for troubleshooting problems, performing maintenance, and ensuring compliance with code requirements. Grounding is an evolving field, and new technologies and techniques are constantly being developed. Staying abreast of these developments can help electrical professionals improve their grounding practices. Industry conferences, trade shows, and online forums are excellent resources for learning about the latest grounding technologies. Grounding plays a vital role in protecting electrical equipment from damage caused by transient voltage surges. Transient voltage surges can be caused by lightning strikes, switching operations, or other disturbances. Effective grounding provides a low impedance path for surge currents, preventing them from damaging sensitive electronic components. In addition to protecting equipment, grounding also helps to improve the reliability of electrical systems. A properly grounded system is less susceptible to voltage fluctuations, noise, and other disturbances that can disrupt equipment operation. This leads to increased uptime, reduced maintenance costs, and improved overall system performance. Grounding is also essential for ensuring the proper operation of electronic devices. Many electronic devices rely on a stable ground reference to function correctly. A poor ground connection can cause erratic behavior, data errors, and even equipment damage. Grounding helps to provide a stable reference point, ensuring that electronic devices operate as intended. In some cases, specialized grounding techniques may be required to address specific challenges. For example, isolated grounding is used to minimize noise and interference in sensitive electronic circuits. Equipotential bonding is used to create a common ground plane in areas where multiple pieces of equipment are interconnected. These techniques can help to optimize the performance of electrical systems in demanding environments. Grounding is a complex and multifaceted topic, but it is essential for ensuring the safety, reliability, and performance of electrical systems. By following the guidelines outlined in the National Electrical Code and best practices, electrical professionals can create grounding systems that provide effective protection and promote the safe and efficient use of electricity. Remember, when in doubt, consult with a qualified electrical engineer or inspector to ensure that your grounding practices meet all applicable requirements. The importance of proper grounding cannot be overstated. It is a fundamental aspect of electrical safety and a critical component of any well-designed electrical system. By prioritizing grounding, we can create safer and more reliable electrical environments for everyone. Soil resistivity plays a crucial role in determining the effectiveness of a grounding system. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable because it allows ground currents to dissipate more easily. Soil resistivity varies depending on factors such as soil type, moisture content, and temperature. In areas with high soil resistivity, it may be necessary to use specialized grounding techniques, such as ground enhancement materials, to improve the effectiveness of the grounding system. Ground enhancement materials are substances that are added to the soil to reduce its resistivity. These materials can include bentonite clay, conductive concrete, and chemical grounding rods. Ground enhancement materials can be particularly useful in areas with rocky or sandy soil, which tend to have high resistivity. Ground resistance testing is a method used to measure the resistance of a grounding system. Ground resistance testing involves injecting a current into the ground and measuring the voltage drop between the grounding electrode and a reference electrode. The ground resistance value provides an indication of the effectiveness of the grounding system. Low ground resistance is desirable because it allows ground currents to dissipate more easily. Ground resistance testing should be performed regularly to ensure that the grounding system remains effective over time. There are several different methods for performing ground resistance testing, including the fall of potential method, the slope method, and the star-delta method. Each method has its own advantages and disadvantages, and the choice of method will depend on the specific circumstances. Fall of potential method is the most commonly used method for ground resistance testing. This method involves placing two auxiliary electrodes in the ground along a line extending away from the grounding electrode. A current is injected into the ground between the grounding electrode and one of the auxiliary electrodes, and the voltage drop is measured between the grounding electrode and the other auxiliary electrode. The ground resistance is calculated by dividing the voltage drop by the current. The slope method is a variation of the fall of potential method that is used to determine the optimal placement of the auxiliary electrodes. This method involves measuring the ground resistance at different distances from the grounding electrode and plotting the results on a graph. The point where the slope of the graph changes indicates the optimal placement of the auxiliary electrodes. The star-delta method is used to measure the ground resistance of multiple grounding electrodes that are connected together. This method involves disconnecting one of the grounding electrodes and measuring the resistance between the remaining electrodes. The ground resistance of the disconnected electrode can then be calculated using a formula. In addition to ground resistance testing, visual inspection should also be performed regularly to identify any signs of damage or corrosion to the grounding system. Visual inspection should include checking the condition of the grounding electrodes, the grounding conductors, and the connections. Any damaged or corroded component should be replaced promptly to maintain the effectiveness of the grounding system. Grounding is an essential aspect of electrical safety and should not be overlooked. By following the guidelines outlined in the National Electrical Code and best practices, electrical professionals can create grounding systems that provide effective protection and promote the safe and efficient use of electricity.